requirements, we may have to have a more precision and less recall, or less, more recall and less precision. So that can be achieved by playing with the threshold. So if you look at this example, by default at 0.5 threshold, the model is predicting like this. When model is predicting, we had got 2 records wrongly predicted. But by changing the threshold manually, right? How do? You take either probability scores or decision scores, probability values or decision scores, and then try to take the threshold you want, and you can actually make the wrong predictions also right. And theoretically, I tried to create a example here, but in real time, right, this is not going to be this ideal, right, ideal. So if you make some one right, others may become zero. Some other records predictions may become zero. So that way, right, it kind of goes here and there on the precision recall scores. So we had taken different thresholds and tried to look at precision scores and recall scores. That code is here. So I have taken decision scores. When you say decision function, right, for every record there will be a decision score, because decision score is nothing but the distance between the record and the decision boundary. Okay. And then when you take a threshold, right, you will get a true or false for every record. True means 1 and false means 0. Okay. Even the algorithm does the same thing, but the threshold for the algorithm is going to be 0.5. At exactly mid, it is going to do it. But if we want to take control over the model and get whatever precision recall we want, so I played with some numbers here, but in reality, there is a method called as precision recall curve. When you pass your y value and the decision scores, it will actually give you precision recall scores at different thresholds. How will it do it? See this here, I have taken 1, 2, 3, 4, 5, 6, 7, 7 different thresholds and try to find the precision and recall scores. You can take n different thresholds, right? If you have 32,000 records, you can take 32,000, maybe 33,700, 379 records are there. You can take 33,700, 379 different thresholds, right? So if you know the minimum threshold and maximum threshold, you can say lin space, right? Did you get it? If you know minimum threshold and maximum threshold, you can say lin space, and then how many numbers you want, this many numbers you want, right? There is one more threshold extra here, that is the default threshold, 0.5 threshold. Okay, so these are all thresholds, these are precisions, and these are recalls.
So by default, it is taking those many numbers, right? It's an inbuilt function.
Yeah, how many records are there? That many thresholds it will take.
+1.
Yeah, +1.
So is there a way to control that?
You can actually do that, right? You can take thresholds, and then you can actually do maybe in a for loop you need to do it.
No, I mean to the precision recall curve.
Precision recall curve, I don't know. Maybe we need to look into the API. Maybe they have given something there. Control number of thresholds. No, I don't think so. No, we don't have a variable there. Parameter to control the number of thresholds there. Okay. So using these thresholds, right, you can do a line plot, right? This is a plot between thresholds and the precision scores now till -1 only, right? Till -1 means last precision we are ignoring, because one precision and one recall score is higher, right? The default ones, right? It may be the last one. So we are ignoring the last one and then taking the threshold, and so I have taken this black dotted line for precision to threshold, threshold to precision values. Okay, so decision scores on x-axis, that are thresholds on x-axis, and precision on y-axis. So as decision score is increasing, the precision is increasing. As decision score is increasing, recall is decreasing. If you look at 0, right, that's where it actually kind of merged, right? Maybe not even merged, it is somewhere there, right? So 90, kind of 93% precision and around 80% recall by default. But you can look at it, right? You can look at it, and if you want 95% precision and maybe 60% recall, so 60% precision and 90% recall, you can choose a threshold somewhere here. Okay, by looking at this diagram, this graph, you will get a high level picture on where to choose the threshold. Okay, this was a question yesterday, right? So the precision recall curve will give you the clarity on where to choose the threshold. Got it? Sometimes user may ask, I want high precision, but recall should not go worse, right? So we will be choosing somewhere a threshold here, so that precision and recall both are going to be kind of balanced. Got it? Got it?
Yes, sir, but thresholds in the plot, thresholds is actually an item more.
Yeah, that's where we are taking
Precision, again we are cutting it one more, right?
precision and recall. Both are one number more, right? So we are cutting one off. Got it? Let me try to run this all above. Threshold minus 1 is not needed. So that is some range, it is the last threshold, the precision and last recall are 1 and 0. So we are ignoring that and then taking the rest of the ones. Okay. For those other thresholds, whatever the thresholds it shows, the 33,378 ones are the appropriate, corresponding precision to recall scores. Okay, got it right?
Yes.
Now, right, by looking at the graph, you can find, or you can actually write a method like this, write a function that will let you know the, the find out find the threshold for precision. I wrote a method. You can write a method for recall also. What I'm doing here, best precision I'm taking a 0, right? And decision scores minimum I am taking, and then I took the linspace, right? What I'm actually doing manually, instead of taking the precision recall curve and the thresholds, I am doing it manually, right? Linspace, I took minimum, maximum, and only 1000 numbers I have taken, right? Decision scores, 1000 decision scores I generated between minimum and maximum, and looping through, right? And I'm predicting here. Predictions is equal to decision score greater than or equal to threshold. Got it? It's going to be true or false array. Okay? So that is precision, the prediction. So now I can use a precision score method to and pass the actual y and the predictions and calculate the precision score at that threshold. At that threshold, if that is greater than best threshold, I am taking best threshold as the current threshold. Okay, and best threshold greater than or equal to decision desired precision, right? So if you want 99% precision, right, I am passing desired precision, and if the the precision score reached desired one, I am breaking and coming out. With before we take all the 1,000, right? If it is reaching at some threshold, if it is actually reaching the high precision score, I am breaking and coming out. So at 4.3, I got 99% precision. If you look at recall score at that threshold, right? It's a 0.17. Okay, so 99% precision you want, you can, if you want 95% or maybe 98%, I will do. Let us see what happens. So I have to take this threshold. See, recall improved with 1% damage on the precision score. Recall improved almost 100%, more than 150% it improved. If you take 97%, right? What is recall? On the existing positive records, how many are being predicted correctly? Right, so it improved even more. So recall should also be high along with precision. So you need to kind of have a balance there in finding the best threshold and then using that best threshold to make predictions. Now, if I ask you to predict, right, what you will do? I know this threshold, right? If I ask you to predict, this is what you do. The predictions are going to be decision score greater than or equal to whatever. So those are the predictions. See that it improved, right? Out of total, 3,000 records, around 2,000 are predicted correctly. But if you look at the positive predictions, only 74 are wrong out of total positive predictions, right? Got it? We can take control over the model like this. By playing with the threshold, you can take control over the model. So I played with recall also. Any questions here? Good. Can I move on? Okay. So precision recall curve is another method, other way to actually check whether model is working good or not. One should prefer precision recall curve whenever the positive class is rare. Okay. If the data set is imbalanced, right, precision recall curve will show you the problems in it. Okay. So the precision recall curve should be kind of, this line should actually touch this top, the top x-axis and, right side y-axis. If you have gap here, that means model is still not working well. Under the area under the curve is what is the, accuracy there. Okay, area under the curve is high, the model is working good. Precision recall curve is drawn for precision, for precision recall scores found at different thresholds. So if you have to do these dots, right? How did you got this? Uh, how did you got this curve? At different thresholds, right? We will calculate precisions and recalls, and we take those precisions and recalls and do the dots. At first threshold, precision and recall, one dot. Second threshold, another dot. Third threshold, another dot. Fourth threshold, like that. Many thresholds we do. If you have to do a line, right, there should be dots, right? For each dot, there should be an x coordinate and y coordinate, recall coordinate and precision coordinate, right? So these recalls and precisions are calculated by the precision recall curve method, and using those precision and recall the values, right, we are plotting. Okay, area under the curve should be high, and precision recall curve method should be used, or precision recall curve should be drawn when the data set is imbalanced. Right, when the data set is balanced, right, you can do a ROC curve. Okay, receiver operating characteristic curve, we call it as. And there is a method called as AUC score. AUC score and accuracy score are going to be similar. Okay, if you see AUC score, it is 97%. What is AUC score? Area under the curve. See this line? That area under this curve is going to be the AUC score. So it is 97%. If you look at accuracy score, see this 97.09. Right, it's almost almost like accuracy score. So AUC, we call this what we call this as ROC curve, and then AUC score. ROC curve and AUC score are useful only on a balanced data set. And an imbalanced data set, precision recall curve is the best to know the accuracy. Can you guess why? Can you actually think a little bit and um, um, can you answer why ROC, the precision recall curve is better in letting the explaining the imbalanced data set accuracy? Why this is better?
It is based on the confusion matrix.
Sorry, I didn't get you.
It is based on the confusion matrix.
Yeah, confusion matrix. But the point there is, when you look at recall and precision, right, these scores basically look into the positive predictions. The positive predictions is the main focus, right? Recall and precision, both scores, their main focus is on positive predictions, right? How many positive predictions are correct in the existing positive data? How many are correct? When the data set is having minority records, and if you give one to the minority record, if that is working well, this line will come and touch the top x-axis and right y-axis. That way it is good. But if you look at the ROC curve, what we are taking is false positive rate and true positive rate. What is false positive rate? False positives divided by false positive spreads plus true negatives. And true positive rate is recall. So if you look at the diagram here, I think somewhere I wrote it. If you look at this diagram, right, false positive rate is false positives divided by false positives plus true negatives, right? So now how many of the negative records negatively predicted, right? That's out of total existing negative records, how many wrongly predicted? Out of total positive records, how many correctly predicted? Okay, that's a different metric actually. That's a different metric. It is like mm, negative records, um, positive records correctly predicted and negative records wrongly predicted. It's a out of four combinations. I actually said we need to look into four combinations, right? Positives positively predicted, negatives negatively predicted, positives wrongly negatively predicted, negatives wrongly. So we are taking two combinations. This first one and the negatives 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 positively predicted. So negatives positive, but I think this one, right? So these two scenarios only it is considering. Okay, so it is not this focus is not in a single area, that too on a minority class. When you look at ROC curve, but if you look at the precision recall curve, right, the focus is all on this area only, because it is between precision and recall scores. Okay, that way when the data set is imbalanced, You should always look into precision recall curve rather than ROC curve and AUC score. AUC score is going to be almost like the accuracy score. Okay. So accuracy score is not good on a imbalanced data set. Okay. Got it? All are good? Yes, no?
Yes, sir.
Okay. So if we are good, right, I'll go and jump in and try to explain more theory about logistic regression, which is very important for deep learning. Okay. So yesterday, Seshiram asked whether we use the same cost function in logistic regression also. Right? I said that the logistic regression algorithm will try to generate a number which is close to 0 for a record which is, with whose y value is 0. Okay. And then it tries to generate a number close to 1 for the record whose y value is 1. Okay. So in that process, right, while generating that process, in every iteration, it should look into the cost function. Do you remember in gradient descent? In gradient descent algorithm, what is happening? Every iteration, it is trying to find new theta. At the same time, it is looking at the cost. No, it is finding new theta. Right? New theta means a new line, right? A new line, right? New line. It found a new line. It found a new line. But at the same time, it is looking at the cost and slope of the tangent for the cost, and then using that and calculating the next theta, right? So here also, in a logistic regression algorithm also, it should do the same, right? The hypothesis function is good. It is generating a number close to 0 for the record the y value belongs to 0. It is generating a number close to 1 for the record no, the y value belongs to 1. But while doing that, it should actually keep a track, keep an eye on the cost function. Will it use the same squared laws? No. Because if you use the same squared laws, right? See this? That's very complex equation, right? 1 by 1 plus e power minus theta 0, theta 1 and so on, theta n, x minus 1 whole square is the cost function. And this is not a convex function. If you substitute this kind of an equation in place of h of x, it is not convex. And gradient descent always needs a convex function because it needs a slope that actually shows the direction for thetas to move in. Right? Got it? This is not a convex function. So we are going to choose a convex function as a cost function. See this here? Cost function for logistic regression is going to be minus 5 log h of x, right? Minus 1 minus 5 log 1 minus h of x. If you look at the log x graph, see this? It's a it's a curve. It's a curve going downward, right? Log 1 minus x. Brackets. Right? This is actually in this direction. If you sum up these two, see that it's a concave function, not a convex function. If you apply negatives here, it became a convex function, right? So we are going to take in place of x, right? H of x we will take the hypothesis function, right? Whatever x can be anything, but the function is going to be convex. So for logistic regression, the cost function is changing because the gradient descent algorithm needs a convex function. Got it? So minus 5 and 1 minus 5 we added for a reason. I'll explain that in a moment. So minus log 1 by h of 1 by 1 plus e power minus z. This z is nothing but this linear equation. Okay? And again 1 minus 1 by 1 plus e power minus z. That is also a linear equation. Right? So why we added minus 5 and minus 1 minus 5? If y is equal to 1, what is y? Target variable. If y is equal to 1, this term becomes 0. Okay. For the records, the y value belonging to 1, this is the cost function. Okay. For the records, y value belonging to 0, this is the cost function. If you substitute y is equal to 0, this term will go off and this term only will stay, right? Log 1 minus 1 by h 1 plus no h of x. Well, log 1 minus h of x is the cost function for zeros. So we combined both and we got a cost function that is convex. Got it? Why this log loss function? This is called as log loss function. Got it? Any questions there?
So h of x here, logistic regression is 1 by 1 plus e power minus z.
This whole thing is h of x. This whole thing is h of x. Got it?
Sir, we cannot just like that select any random convex method, right? So to come up with this particular,
we can. As long as you have these thetas inside, these your hypothesis function is the function in that function in that cost function, right? You can take it. You can take any convex function. That's where there is a hinge loss, log loss, and other loss functions. We can take.
no, how do we know that what are the cost function we select? That's the right cost function. How do we know
It
that?
should be convex because we know the way gradient descent algorithm works, right? We know how the gradient descent algorithm works, right? We need to calculate derivative with respect to theta, right? The function should be, you should be able to calculate derivative of the function, and the function should be convex. Those are the two rules.
Yeah. So basically, the next question is why. Why it has to be convex?
That is answered, right? Already in this. This is what, right? The gradient descent algorithm. How do you know the direction?
No,
You
okay. Maybe
started.
let me ask you differently, sir. So why any convex function will work? That's not clear. I understand maybe convex is required for the slope to be monitored and to be selected at.
That is the reason, right? Whatever you are saying is the reason.
Okay.
Slope to be monitored and slope to be right. You started somewhere here and you need to move in this direction only, right? So that slope will show you the direction, because at the bottom of the pit the slope is going to be 0. When you reach 0, the theta will stay there and the equation will stay there, and you will be fitting the data with best fit line. I am taking the linear regression because it is easy to understand. Same thing will happen on the logistic regression also. In logistic regression, it will do a decision boundary between two classes. This line is going to be a line between two classes where the cost is low.
Okay. Sir.
No, not connected. I think you know both the pieces, but you are not connecting them.
Yeah, I understand that for get to a point where slope becomes zero, we need a.
Suppose, let me ask you a question. Suppose you did not take a convex cost function. How will you know that the theta should move in this direction only?
See, okay. The curve, let's say if we select a curve like some S kind of thing or
Yes,
maybe a
sir.
wave kind of thing.
Yeah, yeah.
Uh,
Wave kind of thing. Then how will you know where is the minimal error? Right? If you take wave, right, what happens? Let me try to draw. I think that's a good, right? Why not? You're asking why convex. I am saying why not convex.
yeah, exactly. Yeah.
Yes. So if your cost function is like this wave, right? Right, you took a cost function like that. So there are many minimas, right? Here there is minima, here there is minima, right? But the you never know. Maybe the curve may come like evenly like that, right? Or it may actually go like that. If it goes like that, right, what happens? This is minima, this is minima, this is minima, this is minima. Where anywhere it may stuck. It may stuck at here, it may stuck at here, it may stuck at here, it may stuck at here. But this is the best. Right? If you run the algorithm 10 times, you may get different results, 10 different results, because there are many minimas. Right?
Yeah, okay, sir.
Got it or
Yeah.
yeah. You think about it a little bit. Maybe we'll discuss again that if needed.
So
It
is
cost.
there any other convex function?
Yeah, there are, hinge laws and other loss functions are there, but log loss is the most prominent one we are going to use in either deep learning or the machine learning. Hinge loss is also used in SVM and the logistic regression also. But when you use log loss, right, you will get probabilities. When you use hinge loss, you will get only decision scores, no probabilities. The implementation is like that, in the scikit-learn, the implementation is like that. Why? I don't know. They actually implemented it like that.
In linear regression SGD also, is there any? So we are actually
In
taking
only
a
squared
least
loss.
square.
There it
Least
is
square.
only squared loss. Only squared loss there is. Okay. Good. So whatever analogy I showed, in the Google thing, right? So when you combine those two, right, it becomes a convex function, and that's where the cost function is taken like this. And now, right, when y is equal to 1, the cost function is going to be log h of x, and when y is equal to 0. So for different records, there is different cost function, but when you combine both, right, it becomes a common function for whole data. Okay. Now let us try to understand how exactly the gradient descent algorithm works in logistic regression. The way it works in logistic regression is a bit different. Okay. And we call a term called as forward propagation and back propagation. Okay, this is very important in deep learning, right? Forward propagation and back propagation. So when you pass your x1 and x0, right, they are the input values. There will be some random b and random w1, right? Theta 0 is called as b here, biased the coefficient, and then w1, right? Instead of calling theta 1, I am calling it as w1, just notational difference, that's it. Okay, so x0 is 1 for all the records, it's a bias term. X1 is the value, right? B is the coefficient of x0, w1 is the coefficient of x1. When the gradient descent algorithm starts, it starts with a random w1 and random b. Okay. To calculate logistic regression, what we need to calculate first? We need to calculate the linear combination. This is called as linear combination of inputs. Linear combination of inputs. And then substitute that linear combination into 1 by 1 plus e power whatever this value minus of. Okay. That is going to be logistic regression. Right? Logistic outcome A. Okay. And then cost function is going to be the difference between A and Y. Right? We would have found something with random W and B, some value, and we are going to calculate cost. We are going to use this log loss function to calculate the cost. Right? That is called as forward propagation. You took random values, right? found out the linear combination, substituted that into logistic function, found out the logistic value, substituted that into cost function and found the cost. That is forward propagation. Now you need to tweak this W, right, and B, right? In our linear regression, what we were doing, theta 1 is equal to theta 1 minus alpha into derivative of the cost function with respect to theta 1. Okay, theta 0 is equal to theta 0 minus alpha into derivative of cost function with respect to theta 0. Right, that's what we are doing. There, the equation was very simple. Right, in linear regression, the equation was very simple. In a way, right, I actually took that j of theta is equal to, I took like theta x minus y whole square, right? And it is theta square x square plus y square minus 2 theta xy, right? So this is a direct equation in terms of theta. But if you take the j of theta in a logistic regression setup, it is a very complex one. Minus y log 1 by 1 plus e power minus w1 x1 minus theta, or plus b in brackets. Okay, minus 1 minus y into log 1 minus 1 by 1 plus e power minus w1 x1 plus b, right? So this is how it is, and it's a very complex equation. If you want to do a derivative with respect to theta, right, it's going to be very difficult, right? In this setup, you cannot do derivative. Hence, you need to use chain rule, right? In chain rule in derivatives. So, what is chain rule? Right? When you change W, right? When you change W1 or B1, the first equation, the first function which is going to get affected is Z, right? So, actually, derivative means the rate of change at which the function changes when the values are changed, right? If you change 1 unit in W1, how many units in J will change? That's what we are going to calculate. So we need to find out when you change 1 unit in W, how many units in J will change? That's the point we need to calculate. Derivative of cost function with respect to theta means when you change 1 unit in W1, how many units in J the cost function is changing? Right? If you know that, accordingly you can go down or go up in the graph, right? So to find out how many units J is changing, there is a cumulative effect, right? When you change W1, Z will change. When Z changes, A will change. When A changes, J will change. So now we can calculate that whole thing, right? When derivative of the cost function with respect to theta can be calculated like this. dz by dw1 will give you the rate of change z changes, right? dA by dz will give you rate of change when z changes, right? Rate of change in A when z changes. 1 unit in z change, how many units in A is changing? And derivative of J with respect to A will give you a change, 1 unit in change, how many units it is changing in J. Okay, why are we doing, why are we calculating individual derivatives and then multiplying? It becomes easy. If you look at this equation, this is in terms of W1. You can directly calculate derivative. It becomes x1 plus 0. Okay. If you look at this equation, right, 1 by 1 plus e power minus z, right? If you try to do derivative with respect to z, it is going to be easy. Right? Again, the cost function is going to be minus y log a, right, minus 1 minus y log 1 minus a, right? What is a? This function, right? Now you want to do a derivative with respect to a, it is going to be easy, right? So you are actually trying to calculate this derivative of cost function with respect to theta in steps, 3 steps, and then multiplying all of them to find out the final derivative. Got it? It becomes easy. When you are trying to calculate derivative, if the equation is in terms of the with respect to variable, derivative of z with respect to w1, z is in terms of w1, right? Derivative of z with respect to b, derivative is in terms, the equation is in terms of b. Derivative of a with respect to g, the equation is in terms of z, right? Derivative of j with respect to a, the equation is in terms of a. So it becomes easy to calculate derivative, and then you are multiplying all of them and calculating the final derivative. Why final derivative? It is always, in gradient descent is always the next w is equal to current w minus alpha into the derivative of the cost function with respect to whatever the variable you are actually trying to do, right? Whatever the parameter, w1, w2, w3, wn, you will do wn number of calculations there. Got it? This calculation, right? This calculation is called as back propagation. Calculating derivative of cost function with respect to theta, calculating like this is called as back propagation. Forward propagation is calculating the j of theta in the forward direction. And once you know the j of theta, right, you should calculate the derivative and calculate the next w. Again, you do forward propagation. Calculate the next w. Again, forward propagation. Calculate next w. Again, forward propagation. Like that, the algorithm will do these calculations until it reaches, this whole multiplication becomes 0, or the derivative of the cost function with respect to 0 with respect to the w or theta or b becomes 0. Once this becomes 0, right, w will stay as it is, where it is. That means it reached the global minimal error place, right? The global minimal error place, right? Got it? How a gradient descent algorithm works on a logistic regression function. Using chain rule, it is going to calculate the slope of the tangent at a given theta or w. Got it? Any questions?
So what is A equal to sigma of Z?
This is a notation actually. Sigma, the sigmoid function, right? 1 by 1 plus e power minus a or minus g is actually represented as sigma z. Not clear?
Okay.
Not clear?
Yes, not clear. Z is equal to W1x1 and Bx0.
W1x1 Bx0, that's it.
Okay, Z and
So
A
you
equal.
see sigmoid function, right? Sigmoid of W1x1 plus Bx0 is equal to what? 1 by 1 plus e power minus W1x1 plus Bx0. But if you denote this as Z, right, what happens? You can say sigma Z is equal to 1 by 1 plus e power minus Z. That's it. I am using this one rather than this equation. Got it? It's a notation. That's it. There is
Okay,
nothing.
what is again? Can you please do the same for J of A comma Y?
J of a comma y is going to be, right, what is a here? This is a, right? A is equal to sigma z, right? So a is equal to what? 1 by 1 plus e power minus z. What is cost function? Logistic regression's cost function. Instead of a, if you put 1 by 1 plus minus e power minus g, it's going to be minus y log 1 by 1 plus e power minus z minus 1 minus y log 1 minus 1 by 1 plus e power minus g, right? Instead of this whole thing, I am putting a, right? Minus y log a minus 1 minus y log 1 minus a. So when it is in the a terms, right, you have to do a derivative. You do derivative of with respect to a of this whole thing. It becomes easy. So while implementing the algorithms, what happens is you will find the equations of all those and then substitute values, right? These W1 is a value, X is a value, X0 is a value, B is a value. You substitute them, right? Again, go back and try to do this this thing. You will already have the derivative calculated, and you will use that equation there and try to substitute the values, right? I think I don't have it in this, right? I have it. No, I don't have it. Okay. So you calculate those equations and form those equations and substitute the values, forward propagation, back propagation, forward propagation, like that. In a iterate in a loop, epochs, right? You take a batch of records and then epochs also. Got it?
Yeah. So you said forward propagation. We start with some values with W1 and B. And in backward propagation,
we
what we
calculate
do?
next W.
Yeah, in forward, we take some values for W1 and B, and we
First iteration. In the first iteration,
first
you
it.
take random values and
Okay.
calculate the cost, right? In the second iteration, right, you calculate the next W, right? In the gradient descent algorithm, what is happening? It started with some random theta and then moving, right? Theta is equal to theta minus whatever, right? This derivative value you are calculating. That derivative value you are calculating using chain rule. They call it as back propagation. Simple. When you use chain rule, right, it becomes a very sophisticated and confusing thing. They make it intentionally make it confusing so that you stay there for some time. There is nothing. Here and there you are calculating derivative only. Equation is simple in linear regression. Equation is complex in logistic regression. In logistic regression, the cost function is a function of functions, right? The cost function, the activation function is a function of linear equation. The cost function is a function of activation function. That's where you are doing the chain rule based, derivatives rather than simple derivative. Got it?
Yeah, but for forward propagation, we take values, initial values for W1 and B. For backward propagation, where we start?
Wherever you started, that's the initial value, right? You took 100 here, right? 100 minus whatever the derivative you calculated. And next value is going to be 70. 70 minus the derivative calculated. Next value is 60. 60 minus the derivative calculated. Until the derivative becomes 0, this will go on in the iterative loop, right? Got it?
I think I got the forward propagation, but backward propagation.
See, it is simple, right? Whatever is happening in the linear regressions, gradient descent, the same thing is happening in logistic regression also. Only the derivative calculation became complex. That's it. Did you understood this one? Did you understand this one? We started with some random 100, right? And then what we did, we calculated derivative at that thing and then multiplied with alpha and subtracted, found out the second 70 and used 70 and then calculated derivative at that 70 and applied the alpha and the derivative, right? Slope, found out 50 and 50 again, same thing there also. What is the difference here and there?
So here there is only one terminology. We are actually going forward, I believe, but there forward and backward.
Here also we are doing, that's what I'm saying.
No, here also backward.
The people who find it, right, they make it confusing. Here also we are doing back propagation. They will not mention that here. There they will mention it. Only because it became, the derivative calculation became complex, right? We are feeling it complex, that's it. Calculating next W, next theta is the back propagation. Got it? In a layman's terminology, calculating the next theta is the back propagation. Got it? Where do you see forward propagation in this diagram? Do you see forward propagation in this diagram?
So forward propagation is nothing but just finding, starting with W1 and B, and then calculating.
Not just starting, sir. Every iteration, finding out the cost or finding out the predicted value is the forward propagation. This is forward propagation. Finding this line is the forward propagation.
Each J value. J of A.
J value, maybe, right?
J of
J
A.
value. Maybe J value. You can think it as J value or prediction also. The finding this line is the forward propagation. Finding out next theta is the back propagation. That's it.
Okay.
Finding next theta is the simple term. They put a forward propagation, back propagation, feed forward network, right? These are all different terms people use to make themselves big. There is nothing big. Got it? Still confused?
So,
Terminology.
yeah. So finding the next theta is called
Back propagation.
backward propagation. So forward propagation.
Finding out the cost, using the found theta, you are going to substitute that into the equation and find out the prediction and the cost. That is forward propagation.
Okay.
Every iteration, there is a theta, there is a prediction, there is a cost. We are trying to reduce that cost. We are making prediction, reducing cost, making prediction, reducing cost. Finding new theta, making prediction, reducing cost. It is just a simple thing and single thing. We are actually finding the next theta, calculating the prediction, and then finding out the cost. That is simple thing. There is no forward, there is no backward. It is all junk. It is all terminology, jargons, right? Right?
I think people confuse it, sir. Actually, because fundamentals we learned very correctly. Now they are adding new words, so that's where we're getting a little bit confused. Now it's clear.
But we need to understand the terminology also, because people, right, they don't see what you know or what you can do, how show off you do, right? How your makeup and how you suit boot, right? So we have to learn all this. Okay. Terminology is very important. So backward, forward propagation back. Some people think there is something going backward. Even I actually put these diagrams. See this? Like a something is going backward. There is nothing going backward. It is just that we are calculating the next derivative. We are using the chain rule to calculate, because the cost function is a function of functions, right? If the cost function is direct function of W's, right? We would have directly calculated as we did it in the linear regression. But in the logistic regression, the cost function is not a direct function of W's. It has got Z, it has got A and all that, right? So we are doing step-by-step calculation. In deep learning, right? This cost function becomes even complex. There is going to be many functions in between the input W and the output. So the chain rule is going to be become too big. That's it. That is, if you understand logistic regression, right? Deep learning you already understood. Deep learning is back propagation, forward propagation you already understood. Simple. That's it. Done. Okay. I'll reiterate the same concept there. Maybe a half an hour thing, right? To recap. But I think you got it. You guys are have got it. Any questions? Okay, good. So logistic regression can be used to do a nonlinear decision boundary also, right? If you look at this is a linear decision boundary, okay? Because the data is like that. A linear decision boundary will suffice, and it will actually make predictions correctly, right? If your data is like this, right? There are some 0 records and there are 1 records like this. You may have to do a circle, right? So algorithm may have to do a circle. So algorithm will actually find out, the equation. The equation, if you put a nonlinear equation in the 1 by 1 plus e power minus e, it becomes a nonlinear decision boundary. Okay, many people doesn't know. They think a logistic regression algorithm is only for linear decision boundary, they think. But nonlinear decision boundary can also be done using logistic regression. You need to remember this. Depending on the equation, it becomes linear or non-linear. How can you do a non-linear logistic regression? Can somebody tell me? How can we build a non-linear, logistic regression algorithm? If you have to programmatically do it, how will you do it?
Oh, you add more degrees.
Yes, that's it.
Yeah.
Polynomial regression. What you are doing? You are actually using polynomial features and adding more polynomial terms, right? Same here also. You convert your data set into polynomial data set by applying polynomial features and then call logistic regression algorithm or SGD classifier. That becomes a nonlinear decision boundary. That's it, simple, right? Got it, other people? Got it?
Yes, sir.
Good. So I will stop here, and Monday we'll have multi-class classification. Okay. Today we saw like yesterday and today we saw binary class classification, and we understood all the fundamentals, right? How to build a model, how to check accuracy on an imbalanced data set, what we should do, precision is good or recall is good, right? When to use what, all that stuff we understood, right? We know everything about classification now. Now we are going to complicate the problem, right? From binary class, we are going to move into multi-class classification. Okay. So now you can take data sets and work. Please make sure you work on data sets. And tomorrow I am canceling the class because most of us may actually stay late and may not be able to wake up and take the class. These classes are very important. And Saturday, Sunday, if you guys are coming to the session, please mention that in the group so that Keshava and Balabhaskar will be available. Rather, they are actually coming and waiting for you. Okay. Please try to make these practice sessions convenient. Actually, Keshava and Balabhaskar are volunteering for the practice sessions. So please make it convenient for them. Okay. So that's it for today. Any questions you can ask? And